Thank you. So this is joint work with with Matti Lasses, Eero Saksaman, and Samuli Siltanen, who are in University of Helsinki. So yes, so in many applications, we like to preserve the edges. So imagine you have a noisy image. We of course want to get rid of the noise, but we don't want to blur it. So we don't kind of want to make soft around the edges. Now in regularization, this is often achieved using something that is called total variation regularization. Now, I'm interested in Bayesian inverse problems where we kind of take a more probabilistic take on this. And the problem is that this total variation regularization, which is often translated into something saying that, oh, we have this formal prior, which is given by the total variation, it doesn't actually, there is no corresponding well-defined random variable that would be this infinite dimensional function space version of it. But of course we would like to have solutions that would look something like this, so that wouldn't blur like if we use a Gaussian prior, for example. Okay, so what we want to do is we want to create priors that behave similarly to the total variation, so they preserve the edges. We want them to be well-defined infinite dimensional random variables. And of course we want to be able to approximate them by some finite dimensional models. And how we do is that we introduce a new random variable, and we say that this random variable lives in a space of trees. So now we will have a prior that is a prior, of course, for the unknown that we are interested in, but it's also dependent on this new tree random variable. And the tree is chosen so that the unknown that we are interested in is usually kind of smoothish or smooth, or kind of what behaves nicely, but it can have some small areas where there can be quick jumps, or it can behave kind of irregularly. So for example, the outline of the panda, koala. Okay, so how we do is we use something that is called Besov priors. Now, there are several ways of creating these Besov priors, but we use wavelet bases. Now, if you have a function, you can split it in this kind of a sum using here the wavelet basis, and then something that we call wavelet coefficients. And these wavelet bases are, for example, we can think them looking like this first one here, which means that in the roughest level, it's kind of comparing the first half of the signal to the second half of the signal. Now, after this, you would take the same wavelet basis, you kind of squeeze it on the half size and rescale it. And you keep doing this. You make it always half of the previous size and rescale it, which means that in the final level, if you have a, for example, discrete signal, you're actually only comparing the difference between 2 pixels. And of course, now we can put this kind of into a tree. So here, on the first level, we would have where we compare to the kind of the first half of the signal to the second half of the signal. On the next level, we would kind of have the squeezed one. So we would be comparing the first quarter to the second quarter and the third quarter to the fourth quarter. And on the final level, we would basically have what's the difference between the 2 pixels. So this is the kind of the trees that we will be interested in. Now, if we then want to create a Besov prior, we need to first define the Besov spaces and the Besov norm. So what the norm is, it says that we take first the LP norm of always on the one layer of the tree, and then we weight it. Because remember, the kind of the deeper we go in the tree, the finer and finer details we have. So we weight it depending on the level, and then we sum over this. And these are now our Besov kind of norms. And if we here choose the P to be 2, this is actually coincides just with the normal Sobolev space. So this is kind of generalizes this Gaussian priors to a much more and much richer framework. But if we then, instead of taking 2 here, we take S and P's to be 1, then this space is quite close to the space of total variation. So if, for example, you think about function that is just 0 when it's negative and x when it's positive, and you take any power of that. You can go as close to 0 as possible, and those are always in this space of 1, 1, 1 space, which means that it almost includes this kind of quick jumps. And those are the sort of functions we want to be included in there. Okay, so then how do we create these priors? Now we have the two questions. So we have the unknown that we're interested in, which is kind of described by the wavelet coefficients, and we have the tree that we need to create. Now the wavelet coefficients, we say that this is quite simple. So we take them coming from this kind of exponential type of distributions. So again, if I take p to be 2, these are just normal Gaussian distributed random variables. If I take p to be 1, this is Laplace or exponential distribution. And those are the two that we are often interested in. So now for the tree then. And this we create recursively. So we take that, we say that, okay, we always take the root node, and we say it's always taken. We then take some number, beta, which is now between 0 and 1, and this says how full we want the tree to be, how often we choose new nodes. Now, we then draw some random number from the uniform distribution. If it's smaller than beta, we choose this new node. If it's larger, we don't choose the node. But if you don't choose the node, you can't choose anything that comes under it. If you turn off the node, you will turn off the whole subtree that is under it. And now you go down. Always if you have chosen a node, you can go down and on the new level and there choose if you take something or if you don't. Now it's easy to see that the larger the beta is, the fuller your tree is, the more nodes you will choose. On the other hand, if you have a small beta, the probability that you draw something between 0 and 1 being smaller than that is quite small, and your tree will probably terminate in some finite level. Okay, so that is exactly the type of priors we want to create. So now, if we summed here over the whole tree, this would be just the normal Besov prior. But now we have the kind of the wavelet coefficient here, which come, you can think, either from the Gaussian distribution or Laplace distribution. But now we sum over only this kind of a subtree. So not the full tree, but only the chosen subtree. And this is now the prior that we are interested in. Okay, so by doing this, we can create priors that can be rougher than, for example, L2. So as long as the smoothness of the prior is chosen correctly, we can get kind of rough priors. But that's something you can also do with Gaussian priors. What we are interested here is that we can actually also study the kind of the fractal dimension of the singular supports of the unknown. So when we are choosing the tree, there are two things that can happen. As said before, now if we choose, in this one-dimensional case, if I choose my beta to be less than half, so less than half of the time I kind of choose new nodes, it means that most probably, with the probability 1, actually, the tree will terminate on some finite level. And if the tree terminates on some finite level, it means that the function it creates have the same smoothness as the basis. Because we use those as a building blocks, and we now have only finite amount of, we are summing over finite amount of them, so the smoothness will be the same. Now, if the beta is greater than half, then again there are two things that can happen. Even if it's greater than half, it can again happen that the tree terminates. And it happens with this probability here. And you can see that the closer the beta is to 1, the smaller the probability for the tree terminating is. Now, if it doesn't terminate, then we know that the singular support of the F, so basically the area where it behaves kind of like really fractally, will have the Hausdorff for the kind of fractal dimension, which is exactly the gamma. And the gamma here was the number that tells how far you are between the half and 1. So the closer the beta is to 1, so the fuller the tree is, also the larger the fractal dimension of the singular support. So the more kind of badly it behaves. Okay, so let's then take a simple example. So now this is just taking a signal f, which have some white noise. Now we can then write this f, we assume for this now a prior, so that it comes from the previous prior we talked, G here is now the kind of the wavelet coefficients, and we assume that they are either Gaussian or Laplace. And the T tilde here tells you kind of the tree that we choose. So we have here the beta being the probability that we choose kind of these nodes, and we now make this recursively so that we don't have any kind of branches that would be hanging in the air. Now, in this case, we can write the posterior distribution, because we didn't have any forward operator other than the identity. We can write the posterior distribution term-wise. So this is really nice, because this means that we can then recursively calculate the map estimator, so the mode for this posterior distribution. Now here, the wavelet density, the beta, has to be smaller than half, because we use it as kind of a regularization parameter. See, we want to penalize against choosing more nodes. We want a sparse solution, which means that we want to put as many of those wavelet coefficients to 0 as possible. So we want to penalize for choosing new nodes. So here is now two things that can happen. If we take our wavelet coefficients coming from the normal or the Gaussian distribution, then we get sort of pruning algorithm where we just turn off or on some of the wavelet branches, but there is no thresholding. So if some branch is chosen, you take all the kind of wavelet coefficients in there, even if they're quite small. On the other hand, if we choose to use Laplace prior for the wavelet coefficients, then we still do this pruning, so we turn some of the branches off. But also inside those branches that are chosen, if the wavelet coefficient is too small, we turn it to 0. So if we look at signal, so here we have this kind of a blocky signal, and we have added quite a lot of noise to it. Now, here is what happens with our algorithm. So here we can see that these are kind of the wavelet coefficients, and the tree kind of, it stays in a tree form. On the other hand, here is I was testing with MATLAB with several kind of inbuilt denoising algorithms, and it seems that for this sort of blocky signal, the thresholding actually gives you the best solution. But it still has these kind of funny spikes in the middle, and it seems to be because we lose some of the kind of a treeness here. So we only have these spikes on the corners, where also here you would have them, but we kind of get rid of these spikes in the middle of the signal, because they are not supported by the surroundings. Okay, so this can of course then be generalized to higher dimensions. So if we now look for a picture of koala, and here is a noised version of it. So here are a couple of random draws if we assume Gaussian priors for the wavelet coefficients, and we use Haar wavelets. Now we can see that this is, yes, we get sharp angles or these sharp edges, but they're too straight. Of course, we don't want the edges to be just straight, so we then tried also doing this with Debussy 2 wavelets, and now we can see that here we kind of have sharp edges, but they're a bit smoother, so this might do better. So here we tried now using the Gaussian wavelet coefficients. So this means that we are now doing just the pruning, and we can see that we get rid of some of the noise, but some places we still have this kind of a sprinkle of noise in the middle of the kind of nice smooth area. And this is because we only turn off the branches, but we don't do any thresholding inside the branches that are chosen. So if then instead we use the Laplace wavelet coefficients, we see that now we actually get rid of also the kind of the sprinkles of funny noises there, because now we can use a little bit thresholding coming from with Laplace prior, but do then the rest of the kind of denoising by pruning. So we don't need to use as much thresholding as if you were doing just the thresholding. So it doesn't smooth that much. Okay, so what we went through is we proposed a new edge-preserving priors. We want them to kind of follow or have similar properties to total variation priors, but also be well-defined and be able to approximate them by some finite dimensional setting. We can calculate the fractal dimension of the singular support of those prior draws. And we can also calculate the map estimators um, sorry, for the signals and image denoising. And if we assume Gaussian prior, then we get this kind of a pruning algorithm. If we assume semi-Laplace prior, so the wavelet coefficient coming from the Laplace distribution, then we get the pruning plus some thresholding. And we can actually also calculate the conditional mean estimator, but of course that won't be sparse anymore because it will kind of give weight for all of the coefficients. Okay, thank you.
Blur of it, right? And you apply this. I mean, obviously you're looking for the edges. Would the ability to discriminate the edges, I mean, depend on whether you're on sort of a vertical edge or you know?
So with
does that affect it?
So with the hardware, it definitely kind of depends a bit on that. But when we go to the Dropper ones, it kind of works out around it. But this one didn't actually yet have this kind of actual inverse problem where we would invert the forward operator, because it shuffles the whole wavelet basis. So we are not yet quite sure how to generalize when you calculate the posterior distribution, some estimators out of it, for the actually inverse problem where we shuffle the kind of everything on the.
Suggestion, I'm not sure if this is right or not, but when I was looking at the trickling down the tree,
Mm-hmm.
and then you get to the node and switch it off, that might have a one-to-one correspondence to a tree with a one dimension bigger. In other words, you just that switching it off becomes like another choice. You go 1, 2, 3. So it's like you might be able to consider a tree with a larger tree, whereas one of your paths is just a node at the end of that tree rather than being an entire path. I'm just not sure if I can do that in my head.
Yeah, yeah, it might be.
Because, you know, switching it off is like another. It's like saying -1 instead
Yes.
of 1, 2, or 1, 2, 3.
Yeah.
Increase the base.
Yeah, yeah, it might work. Yeah. Mm-hmm. So I think it overcompensates for some reason on here. It happens also with the thresholding or self-thresholding, and I tried with the different weights, because this is now actually kind of assuming that the S and P so that they cancel each other and there is no weighting. You can get a little bit less on here if you weight it correctly, but it doesn't fully get rid of it. So I'm not quite sure on what exactly creates on the. But it seemed to be with almost all of the kind of, also with other ones, that it creates the spikes on the edges. Yeah, but why that's happening, how could you get rid of it is another thing on the. Yep.
I wonder if you use sliders to images with classic fractal properties, but is there an application here to sort of other noisy data sets which is the space or the data set which contain noise in general? Is this something that you apply to the wider stuff?
So I think we were kind of, so you get quite a different information out of this, and one would be exactly where to use it would be interesting. So I tested with different kind of fractal dimension images, and it does definitely give you a different sort of amount of how many nodes it needs, depending on the fractal dimension of it. But I'm not yet quite sure how or where we could use it. So there are some kind of where you categorize things based on their fractal dimension, for example, in medical imaging. So I think some cancer cells have, for example, fractal dimension which is higher than a normal. But yes, that's a little bit tricky still on the where to use some of the extra information we get from this.
Okay, well, I think we'll have to carry on. So thank you very much.